Hello everyone, I'm Norman Wildberger. Today we're going to talk about transposes and inverses. So these are important operations on matrices. So transposes act on any size matrix while inverses are only defined for square matrices. That means, i.e., matrices that are n by n matrices. Okay, so we want to talk about these two different kinds of transformations. The inverses are more complicated and important, but transposes act in some ways a little bit like inverses, so it's good to start with them. All right, so what is the transpose of a matrix? Well, it's a kind of a reflection. So the transpose of the matrix is described in terms of its size. If A is an m by n matrix, then its transpose, and it's usually denoted A with a superscript capital T, is an n by m matrix. The rows of A become the columns of A transpose and vice versa. So let's give an example. So if A is the matrix, say 2, 1, 3, 4, minus 6, 17, then A transpose is the matrix 2, 1, 3, 4, minus 6, 17. So you can see that the rows of A become the columns of A transpose, while the columns of A become the rows of A transpose. And A is a 2 by 3 matrix, while A transpose is a 3 by 2 matrix. That's quite simple. And if we wanted to describe it in terms of entries, so an official definition might be, is that if A equals, say, the matrix with entries little aij, okay, is an m by n matrix, then A transpose is the n by m matrix where the ijth entry of A transpose is a ji. In other words, it's the ji'th entry of A. All right, that's a concise way of describing the relationship between the entries of the matrix A and the entries of the transpose, basically interchanging the properties. First of all, that it's linear. If A and B are both matrices of the same size, then A plus B transpose is A transpose plus B transpose. So here, if A and B are both the same size, say m by n. And secondly, that if we take lambda times A and we take the transpose of that, so if we multiply all the entries by 5, well then kind of obviously the transpose of that is going to be lambda times the transpose of A. But a more subtle property is the following, that if A is m by n and B is n by p, then in that case we're allowed to multiply them because this n and that n are the same. Okay, so then if we multiply A times B and take the transpose of that, what we get is the transpose of B times the transpose of A. So when we take transposes, the order interchanges. And that makes sense at the level of sizes, because if we look at the sizes of things, AB itself is, AB is going to be an M by P. So AB transpose is P by M. And on the right-hand side, B transpose is P by N. Just reverse these ones. And A transpose is N by M. Reverse these ones. So B transpose times A transpose is, now these N's here also agree, but the other elements are P and M. So we get P by M. So this dimension of AB transpose agrees with the dimension of B transpose times A transpose. Okay, so let's see if we can prove this. We're going to prove the third one. The first two are almost like exercises, but the third one is a little bit trickier. So let's prove this third property. Proof 3. Okay, so A is M by N and B is N by P. So let's have a look at the ijth entry of AB transpose. Okay, the ijth entry of AB transpose. By definition, that's equal to the jith entry of the product AB. So that's the definition of the transpose. Now, what is the jith entry of AB? So I remind you that A is, we're assuming it's M by N, and B is N by P. So this is jith entry. It's the sum from K equals 1 to N of the jkth entry of A times the kith entry of B. But this is then also equal to the sum from K equals 1 to N. I will write it with the B's first. B ki A jk. And then I'm going to write this as the kith element of B is the same as the ikth element of B transpose. And A sub jk is the kjth element of A transpose. And when we write it that way, now we see that this is the, altogether, it's equal to the ijth entry of B transpose times A transpose. Because there's a common index there, and the outside indices are I and J, and we're talking about the matrices B transpose and A transpose. So that's the computation that shows that the transpose satisfies this pleasant condition up here. When we take the transpose of a product, we get the product of the transposes, but in the opposite order. Now, another role for transposes is to have a look at the dot product in matrix language. So the dot product of vectors in matrix language. So we now have an opportunity of sort of rethinking what the dot product of vectors is. So I remind you that if you have two vectors, say if A is an element in n-dimensional space, that means it's a column vector of length or of size n, and B is also in Rn, then we can define the dot product. Then A dot B is a number. Okay, and more specifically, if A is equal to A1 down to AN, and B is B1 down to Bn, then I remind you that the dot product of these two vectors is the sum A1, B1 plus all the way up to AN, Bn. All right? Coming from vector geometry. Now, we can interpret column vectors as matrices. Okay? So, but a column vector in, say, Rn can be viewed as an n by 1 matrix. Right, this vector here is essentially a matrix with n rows and 1 column. Now, similarly, a row vector, which typically we usually write maybe something like, v1, comma, v2, comma, vn. So this is what a row vector looks like. This can be interpreted or recast as a 1 by n matrix. Okay, in that case we write without commas. When we write matrices, we generally do not have commas. So we would write this row vector rather as v1, v2, v2 up to vn without any commas. So this way, both row vectors and column vectors can be sort of brought into the realm of matrices, with column vectors being n by 1 matrices and row vectors as being 1 by n matrices. So now, if we look at our two original column vectors, so A equals A1 down to AN, and B equals B1 through Bn, then let's have a look at this following product. When we take A transpose times B, so the transpose of A will be the row vector A1 up to AN. B is the column vector B1 down to Bn. And when we multiply them, we're getting A1, B1 plus all the way up to AN, Bn. Actually, we're getting that as a 1 by 1 matrix, but if we don't bother with the brackets denoting the 1 by 1 matrix, then we can interpret this as just the dot product of A and B. So we've maybe established a little proposition, is that if A and B are column vectors, both n-dimensional, then the dot product between them is just A transpose times B.